Hello! We are starting a new section on planar graphs. These are graphs that can be drawn on the plane without edges crossing each other. The main goal for the planarity section is that we will prove Kuratowski's theorem and other characterizations of planar graphs. Along the way, we will prove other interesting results about planar graphs as well. We start with some basic definitions. A graph is planar if it can be drawn on the plane so that edges only intersect at common endpoints. The drawing itself is called a planar embedding. For example, K4 is a planar graph, and this is an abstract structure of vertex and edge sets. And K4 is planar because there are some planar embeddings of the graph, like these two. So we make a distinction between a planar graph and a planar embedding. A graph is a structure of vertices and edges, and an embedding is a drawing. To make things clear, we will make this definition. We use plane graph to refer to a planar graph along with one possible embedding. We use points and lines to refer to the representations of vertices and edges in the embedding, respectively. Though sometimes we might still use vertices and edges when talking about a plane graph. Now, a rigorous discussion of planarity involves topology, but topological details are outside the scope of this course, so we will take many topological results for granted. We will mainly focus on the combinatorial aspects of planar graphs. We will give you a small taste of topology in the following definitions. A curve is a continuous image of a closed unit line segment. Such a curve is simple if it does not intersect itself. Here is a representation of a unit line segment, and here is a curve. And we are mapping the two ends of the line segment to the two ends of the curve, and the points in the middle can be mapped accordingly. This is a simple curve. On the other hand, this is not a simple curve, because it has an intersection. A closed curve is a continuous image of a unit circle. And here is a representation of a circle and a closed curve. And we are mapping the points on the circle to the closed curve in a continuous fashion. Now, curves and closed curves are important in a plane graph. That is because an embedding of an edge is a simple curve, and an embedding of a cycle is a simple closed curve. Now, in a planar embedding, we may divide the plane into several connected regions. And the way we define this is the following. A set of points on the plane is arcwise connected if any two of its points form the endpoints of a curve that is entirely inside the set. For example, for the points in this green shape here, we can take any two of its points and find a curve that is entirely inside the green shape. So this shape is arcwise connected. Later, we will use this to define faces. Now, one of the main things from topology that we will assume for granted is the Jordan curve theorem. The theorem states that any simple closed curve in the plane partitions the rest of the plane into two arcwise connected open sets, one inside and one outside. This seems like an obvious result, but it does require proof, which we will not do. Now, there are a few definitions related to a simple closed curve. Given a simple closed curve C, the open set of points inside C is the interior, denoted by int of C. The open set of points outside of C is the exterior, denoted by ext of t. Now, these two sets of points do not include the points that are on the curve C. If we want to include C in these two sets, then they are the closed sets denoted by capital int of C and capital X of C, respectively. Here is an example of a closed curve C, its interior, and its exterior. We note that the Jordan curve theorem implies that any curve that joins a point in the interior of C with a point in the exterior of C must intersect C. And you can explain why this is on your own. We will now use the Jordan curve theorem to prove a simple result that you may have seen before. And that is that K5 is not planar. And here is our proof. We suppose, by way of contradiction, that K5 has a planar embedding. We let the vertices of the K5 be V1 to V5, and these would be 5 points on the plane. We now look at the lines joining V1 to V2, V2 to V3, and V3 to V1. They form a simple closed curve C, because it is a cycle in K5. Now the point V4 is either in the interior of C or the exterior of C. Without loss of generality, we assume that V4 is in the interior. Then, the lines V4 to V1, V4 to V2, and V4 to V3 are also in the interior of C, except at their endpoints V1, V2, and V3. This looks obvious that they are in the interior, but you could try to explain why that is. We now let C1, C2, C3 be the closed curves formed by the cycles V2, V3, V4, V1, then V1, V3, V4, V1, and V1, V2, V4, V1, respectively. What we are doing is that Ci would avoid the vertex I. Notice that for each of the interior of Ci, it is a subset of the interior of C, and more importantly, Vi is in the exterior of Ci. So V1 is outside of C1, V2 is outside of C2, and V3 is outside of C3. We now look at the final vertex of K5, which is V5. Can you see where the point V5 is located? We know that there is a line joining the point V5 to each of the points V1, V2, and V3. And because Vi is in the exterior of Ci, that means that by Jordan curve theorem, V5 is also in the exterior of Ci for each I. This means that V5 is in the exterior of the larger curve C. Can you see why this is a bad thing? This is bad because there is a line joining V5 and V4, where V5 is in the exterior of C and V4 is in the interior of C. So it must cross C by the Jordan curve theorem. And this is a contradiction. So K5 is not planar. And that completes our proof. Now similarly, you can prove the following. K33 is not planar. Now we specifically mention K5 and K33 here because K5 and K33 are the key graphs in Kuratowski's theorem. They are essentially the only things that could cause a graph to be non-planar. To make this more precise, we have the following definition. A subdivision of G is obtained from G by replacing each edge with a new path of length at least 1. This means that we may introduce vertices of degree 2 to the edges. For example, here is a K4, and this is a subdivision of K4. And this is a K5, and a subdivision of K5. Now, the reason why subdivisions are important is because they preserve planarity. And here is a key proposition about subdivisions. A graph G is planar if and only if any subdivision of G is planar. And the idea is that an edge and a path are both represented by a simple curve. So essentially, a subdivision has the same shape as the original graph. If you can draw one on the plane, then you can draw the other on the plane as well, and vice versa. So combining this proposition with the fact that K5 and K33 are not planar, we get the following result. Any graph containing a subdivision of K5 or K33 is not planar. And Kuratowski's theorem states that the converse is also true. A non-planar graph must contain a subdivision of K5 or K33. This is a long proof, and we will prove this a little bit later. And that is the end of this introduction to planar graphs.